Hey folks, and welcome back. So today we're going to be doing a recap of the metals topic that we started with just before Christmas, just to remind yourself of what on earth we did then. So let's get started. This little table just explains some of the properties that metals have, going down from, we've got strength, thermal conductivity, electrical conductivity, malleability. What that means is just means you can make different shapes, so like your pots and pans to jewellery to components of your mobile phone. And then ductility at the end is being able to draw into wires. So again, if you've got a metal fence, if you've seen a metal fence, basically just long thin strips of metal that can be used to kind of support buildings and different structures. So we're going to learn a new type of bonding today called metallic bonding, and we've got a nice little diagram here of a grid with some nuclei and some delocalized outer electrons. So what is metallic bonding? Well, as I've said at the top, electrons in the outer shell of a metal are not held tightly in position. They are said to be delocalized electrons. And basically, the definition of a metallic bond is what I've got here. It's electrostatic, so that means charges, force of attraction between a positively charged ion and delocalized outer electrons. Now in my little diagram, these little E's represent electrons, and they're supposed to be kind of whizzing around the structure, just to indicate that they aren't stuck in place, that they can move kind of all around really. Metals take part in different reactions. We're going to have a look at 3 of the different reactions today, and what we can do is we can compare the rates of reaction from experiments to be able to place the metals in an order, and we can call that the order of reactivity. Can also be called the reactivity series. Something very similar called the reduction potential series is on page 10 of the databook. So it's worth having a look at the databook just to see this table at the end. This is something that you'll take into any tests or any exams that you're doing in National 5, so it's worth being familiar with it. It's just the last page of your databook. So we're going to start with reactions with water. At the top it says metals are insoluble in water, so quite a lot of metals don't react at all. You can find this in the databook. If you want to go to page 8, you'll see a big table at the bottom with metals going down the left hand side and the end of your compounds going along the top, going towards the right, so like oxide, hydroxide, carbonate. And what you'll do is you'll find the metal, go along to the section you're looking for. You'll see symbols that say V, S, S and I, or a dash. VS means it's very soluble, S means soluble, I means insoluble. There is a little table at the bottom, a little key that can explain that. So that's how you would find if something is soluble or not. And if you get a metal that does react, it makes a metal hydroxide, which is called an alkali. If you think back to first and second year, you would have done acids and alkalis. That's what an alkali is. And hydrogen gas. Now you can actually predict if it's hydrogen gas by testing it. So a gas test for you is hydrogen ignites. It also burns with a pop. So you can identify it with a squeaky pop, and that is your test for hydrogen gas. So if we take the general equation, metal plus water gives us metal hydroxide and hydrogen, we can do a chemical equation, and then from that we can do a balanced equation. So let's start with, say, magnesium. So you've got magnesium plus your water gives you magnesium hydroxide. And hydrogen as well. So what we can do is we can write our chemical equation from that. Magnesium's just got the symbol Mg, water, or what we all know as H2O, and magnesium hydroxide. So what you would do is you go to page 8 in the data book, you would see that hydroxide has got a valency of 1, magnesium's got a valency of 2. So if you swap and drop them over, you've got MgOH2. Now I've put the OH in brackets. If I didn't do it in brackets, then hydrogen would have a valency of 2, or would have 2 of them, which we don't really want. And then don't forget hydrogen on its own is H2 at the end. If we have a look at balancing it, so let's change colour. Magnesium, we've got 1 on the right hand side and 1 on the left. Hydrogen, we've got 4 of on the right hand side and 2 on the left hand side. And then we've got 2 oxygens on the right hand side and not on the left hand side. So all we need to do is put a 2 in front of our H2O, and that is our equation balanced. Now I've also got a little tip at the end to help you remember this one. It's all the metals that end in IUM, really, that react with water on that table on page 10 of your data book. If we move on, we can do reactions with oxygen this time. So oxygen can be made in the lab by heating up potassium permanganate in a test tube. Now potassium permanganate is a lovely purple kind of solid that you dissolve in water to make this beautiful purple solution. It is basically what we could use in a lab to make oxygen. It also provides more more oxygen in the air than air. That's why we add it to reactions. And you would do this experiment, you would hopefully see your metal glowing brightly, or when we did it, I used filter paper at the side and we did magnesium to make a lovely bright glow at the end when it went on fire, and we also had a flame test as well. So metals react with oxygen to make a metal oxide. Let's pick a different example this time. Let's go for aluminium. Plus oxygen gives us aluminium oxide. Let's write our chemical equation. Aluminium is just simply Al. Oxygen's O2 because it's a diatomic element. If you go to the data book, you'll see that aluminium's got a valency of 3. Oxygen has a valency of 2. So if you swap them over, you've got Al2O3. Now to balance it this time, this one's a little bit more tricky. We've got 2 oxygens on the left hand side and 3 on the right hand side. Now you can't really get anything that will kind of go into them easier, so what we can do, if we times it by 3 to get 6 oxygen on the left hand side, and then times it by 2 on the right hand side to get 6, that'll help. So let's put a 3 here and a 2 here. What that means is we've now made 4 aluminium over here, so we can just pop a 4 in the front, and there is your answer of your balanced equation for aluminium and oxygen. And finally, we're going to have a look at reactions with acid. Now if you go back to the unit 1, we know that metal hydroxides, metal oxides and metal carbonates all neutralise acids because these are all bases. So some of the most reactive metals can also neutralise an acid. They produce a salt and a hydrogen gas. If we take our general equation here, metal plus acid gives you salt plus hydrogen. Let's pick an example. So let's go with lithium. And let's go with hydrochloric acid this time. I could have picked nitric acid or sulfuric. Now to make your salt, it's the metal is the first part of the name, and then the ending is the acid that you've used. So we've got hydrochloric acid, so that makes chloride at the end. Sulfuric would make sulfate, and nitric would make nitrate, and then don't forget your hydrogen at the end. So let's do our chemical equation, Li plus HCl. Lithium chloride, they're both got a valency of 1, so it's nice and easy. You've done all of that, you can make your reactivity series by comparing all the different experiments that we would have done in class, or we have done in class, into a lovely table so that you can understand which metals are more reactive than others. Here we have our reactivity series. As you can see, we've got metals on the left hand side, and then our reactions with oxygen, water and acid. Quite a lot of metals actually react with oxygen to form your metal oxide. Slightly less react with acid to form your salt and your hydrogen. And then if you have a look, water, there's very few that react with water. Some react with steam, so you're basically trying to force the reaction to happen, and then quite a few don't react at all. Remind you what on earth we did before we move on to the new part of metals, where we have a look at terms called oxidation and reduction.